Are you on your head, for example, or are you rotating? Those perceptions need to be sent to the brain, or the input, stimulant needs to be sent to the brain. And that's sent to the vestibular cortex, again, in the insula. Okay. Multimodal association area. So, I described to you, for example, you see something. And the first input, the stimuli of seeing it, goes to the primary visual cortex. And then to be able to understand that vision a little bit better, to say, oh, that's a flower, we would use the visual association area. I also described how we would smell, right? Through the olfactory cortex, and how we have an olfactory association area to help us interpret that as being a pleasant smell, a bad smell, or whatever the case may be. Well, does it surprise you then that with all the different senses, we have a larger association area that can take more than one sense and put it together? That's where we're going. Okay? So multimodal association area is going to take a lot of different things and put them all together. Okay? For example, smelling and hearing. Okay? Taste and other things. So we call that the multimodal association area. And we have three areas. I want to make sure I said that right. Three areas we'll talk about today. Three. The first one is called the anterior association area, or what a lot of people call the prefrontal cortex. The anterior association area, or prefrontal cortex, is this part of the brain right here. This is the part of the brain you don't want to hurt. Okay? This is what many people call the brain. When people say you don't have a brain, okay? You're not smart enough, you don't have the right intellect, your personality is horrible. Well, that's the part of the brain you should blame, right? It's also the part of the brain that gets damaged with, well, I used to damage that part of the brain on purpose. You ever heard that? Back in old days. You ever seen One Flew Over the Cuckoo's Nest?
Yeah, the lobotomies.
That's lobotomy. They damage that part of the brain.
It's also, motor vehicle accidents, anytime where you've got that rapid deceleration.
Yeah. So the anterior association or prefrontal cortex is where a lot of our intellect and personality is really where it all is. Our intellect, our personality, our reasoning, our deductive skills, our memory, our understanding of abstract ideas, planning, all these very highly intellectual things get done right here. It's called the prefrontal cortex. And again, it's the anterior association area. The posterior association area, I can't really point out to you because it's kind of all over this area. Big surprise. And not here, this is a different part of the brain, but over here, in the cerebrum. Okay. The posterior association area is involved in taking all those things we talked about, the sensory perception of hearing, of seeing, of feeling, let's say, other senses, and gives it into one big picture. So let me give you a good example of this. If I have a jar or a beaker of acid, okay? I'm not going to do this, obviously. And I drop that acid and it hits the ground, explodes, the glass shatters everywhere, and acid sprays all over the floor and all over my shoes and all over my pants, right? And you start to smell burning of clothes, of leather, of flesh, because the acid is burning. And you might see some smoke or other things occurring, right? That idea of seeing it, hearing it, crash, smelling it, all putting it together, that big picture is what's being done here in the posterior association area. Okay? So again, that's the visual thing I usually use with that. The limbic area, which is the last part we'll talk about, or what we call just generally the limbic system, is emotional. We're going to put an emotional component to it, which is, oh my gosh, I'm in danger. My feet are burning away, right? There's a sense of danger, a sense of urgency, an emotional response. So we'll talk very generally about emotions later on. And the limbic association area, or what people just call the limbic system, is involved in that. And again, it's many, many parts of the brain that kind of work together for this. Okay? So that's a multimodal association area. Okay so far? So on page 10 it says there's a lot of words there under lateralization of cortical function. A lot of words. And I'm going to summarize it very, very quickly. Okay? There is some degree of dominance with your brain, with your hemispheres. But it's not as common or it's not as predominant as people may have once thought. So people used to think, for example, that if you are right-handed, then your left brain is dominant, at least with everything. And that's not really quite true. There is a lot of cooperativity between the left and right hemispheres. And in fact, there is something called the corpus callosum that ensures that. And we'll see this in just a little bit. It's not a term to be familiar with, but I'll show you this real quickly here. So you'll see this in your actual brain when you cut it apart. But this right here is called the corpus callosum. There's a physical connection that connects the left and right hemispheres together, so they work together. Right? That's the idea. You want the left and right hemispheres working together to give you one general cerebrum. But there is some degree of dominance with one side versus the other in things like language. So there is some degree of dominance, but it's not as common, at least it's not as predominant as people once thought. But there is one thing I'll mention with this, and I'm sure you've heard this, or if you haven't heard this, now you've heard it from me. If you have a child that is right-handed, or is showing a predisposition to being right-handed, or if you have a child that's showing a predisposition to being left-handed, don't switch it. Okay. There is, again, there's a small degree of dominance where the right half is a little bit stronger than the left, or vice versa, and that shows up in our predominance for which hand we prefer to use. Okay. So a child that is left-handed, which is about 10% of us, would technically have right brain dominance, technically. Okay. Now, what that means is if you force that child to switch it, well, you're really kind of messing with the wires. Easy way to say it. Okay. And so there have been documented cases of learning disabilities as a result of trying to switch kids. So it's not worth it. But 10% of kids are going to be left-handed, and there's nothing wrong with it. There's no difference in intelligence, there's no difference in skills, there's no difference in anything else, other than they have to buy a different glove when they play baseball. That's it. Okay. But just thought I'd mention that real quick. Now, there is some differences in what the right brain tends to do versus the left brain, and again, it's kind of switched through the left and right-handed people. So the right brain tends to be more abstract ideas and artistic, and the left brain tends to be more logical thinking. And okay, there's some truth to that to some degree. But someone who's left-handed just has that reversed. That's all. So we just spent all that time, again, I told you this was going to happen. We just spent all that time talking about the cortex, bullet point A. So we're right here in the cerebrum, we covered the cortex, and we got all this together. We're going to cover the white matter, though, and the basal nuclei very, very quickly. So what is the white matter? Well, it's all the connections, right? So I just described to you how we have the primary areas, and we have the, let's say, the initial association areas, and then we have the multimodal association areas. And then you can also imagine the brain has to communicate with the rest of the body, including the spinal cord. So it makes perfect sense. You're going to have wires, meaning those being axons, that are going to connect to different gyri, as you can see here, or different lobes, as the case may be, or even with different parts of the brain deep to that. And so you'll see all these different wires. And that's all I want to show you here. I don't want to care that you know what they're actually called. They're actually, you can see here, they're actually in italics. So commissures, for example, association fibers, projection fibers. There's different names for these things, that's fine. But the point is, the white matter, what you call the white matter, the reason it looks white is because it's the myelinated axons that are connecting the cortex to the rest of the brain, or even to itself. Okay? That's cerebral white matter. Good so far? Leave it at that. I said before, the basal nuclei. This is a picture you can see here, and you'll see some other ones as well. None of these pictures, by the way, will be on your lab exam, so anytime you see a brain cut up like this, don't worry about it. I'll say it again later on, just so you know. So these are just considered basal nuclei. There's a bunch of different nuclei that are in the cerebral cortex, cerebral hemispheres. And they serve different purposes, different functions. Collectively, for example, one nuclei would have a particular function of the body. They would control particular sensation or something along those lines. We're not going to get into those details right now, but they are organized for a specific purpose. But other than that, that's all I wanted to say. There are basal nuclei deep to the white matter, and again, those are somas. Give you an idea what these do in general. So I have very precise control of my arms and my hands, right? I can do a lot of things. I can manipulate a lot of things. I can put my hand out like this and keep it steady, right? Why? Well, because I have precise control over unwanted movements. So I'm able to keep myself steady and control things in my environment in a very controlled way. Can you think of somebody who wouldn't? Parkinson's. Okay. So Parkinson's disease is a degeneration of the basal nuclei. It's where they are losing that ability to stop unwanted movements, and it's progressive. It gets worse and worse over time, different stages. Okay? And so that movement that you have, especially when you're trying to stand still, okay, is something that is common with both Huntington's disease and Parkinson's. And again, it's caused by the basal nuclei. So it gives you a rough idea of what these are involved. Are we good?
Sure.
Okay. Let's move on just a little bit. Here's another view of that. Okay. Again, this is not a picture that will pop up in your exam. It just has a picture from the very beginning. The diencephalon. The diencephalon. Well, we have three parts that make up the diencephalon from your big picture. We have the thalamus, the hypothalamus, and the epithalamus. So we can imagine the thalamus is kind of in one place. The hypothalamus is below it, and the epithalamus is kind of above it. The reality is it's a little bit behind it. You'll see in a few minutes. So those are the three parts, the three structures. Thalamus, hypothalamus, and epithalamus. Now the thalamus, I'll show you a better picture. This picture and this picture are the two that I would definitely use on your exam to possibly show you this, possibly this as well. Okay? So I'm going to come to this picture first. Okay? I think this is a nice one to show you what we're talking about. So large egg-shaped structure. See one here and one here. So we have a thalamus. What is inside that? Well, we have a bunch of nuclei. Okay, what's a nuclei? Well, it's a collection of cell bodies. So if you actually look at one of these egg-like structures, you can see it right here. A bunch of different nuclei. Each one of these is devoted to some other sensation. And we're going to get to that in just a few minutes. Okay? So basically, this is full of a bunch of nuclei. And we call that a thalamus. Okay. The best way for me to describe what this is this picture right here. I'm going to go forward a little bit to show you. When we talk about ascending tracks, right? We're talking about tracks that are going up the cord that are involved in sensation, right? And I said that they're going to be traveling up the cord, and the majority of them are going to synapse in the thalamus. And then once they're in the thalamus, they're then going to be routed to the various different parts of the cerebral cortex, in the surface of the brain here, depending on the type of sensation they are. So quite literally, the thalamus is the gateway to the cerebral cortex. So you can imagine that a sensory neuron would come up here and synapse with one of those nuclei that's inside the thalamus, depending on the type of perception or sensation or whether it is. And then it would get routed to various different parts, depending on whether, for example, it was vision or possibly hearing, etc. Make sense? So it's the gateway to the cerebral cortex. That's why I have that underlined on page 14 if you didn't see that. This picture right here is a good one. for me to show you the hypothalamus. But first off, right here, this is the thalamus right here. Okay, it's hard to see without it being color-coded, but it's right here. This is the hypothalamus right here. So it's just below that. And the epithalamus is right here. Okay? So this is the hypothalamus right here. And this is what we call the pituitary gland. We'll come back to this in just a few minutes. So the hypothalamus, again, is located below the thalamus, and it's involved in a lot of things. The hypothalamus is something you should be familiar with in greater detail than the rest of the part of the brain we just spent a little bit of time on. So we'll talk about that in just a few minutes. It has nuclei in it, and again, each of those nuclei serve a particular function, but we're not going to get into all those different nuclei today. It just gets too complicated. I would just rather have you understand the general, or let's say the specific functions of the hypothalamus, which we talk about on page 15 in just a few minutes. Just below that, there's something called the pituitary gland. And other than pointing out the pituitary gland, that's all I'm going to do. Chapter 17, which is what you do in 102, we'll cover that in much more detail than I'm going to. You justify that. Okay? There are different secretions, different hormones that are produced by the anterior and posterior part of this gland, which are way too complicated for me to get into, and that's dedicated for chapter 17. You'll learn about that later. I just wanted to point out part of the brain. So that's the pituitary gland right there. As far as the hypothalamus, I go into a lot of detail here on page 15, and you should be familiar with these things, right? The hypothalamus is the visceral control center of the body. What does that mean? Well, it controls a lot of things. It's involved in a lot of homeostatic balances. For example, it is involved in temperature regulation, which is actually bullet point 3 there. So we talked about in that very first day of class, negative feedback. And we talked about how your house has a thermostat. And the function of that thermostat is to make a decision. If the house gets too cold, it picks it up from that temperature gauge, right, the actual thermometer. That's the actual sensor. But the actual command center, or the control center, right, is the thermostat. It decides, okay, it's getting cold in the house, I better kick on the furnace. Or it's getting too hot in the house, I better kick on the AC. Right? And that's that negative feedback that keeps it within a homeostatic range of, let's say, 68 to 72 degrees in your house. Right? So that's what happens in the brain. The hypothalamus is the part of the brain involved in temperature regulation. So what makes the decision that you sweat? It's your hypothalamus. What makes the decision that you're going to shiver? It's the hypothalamus. It's just going to control temperature regulation. It's also involved in a lot of other things as well. We call the autonomic control center. So your blood pressure, is it high or is it low? In a given moment, is controlled by the hypothalamus. Your heartbeat, is it fast, is it slow? That rate is controlled, again, by the hypothalamus. Now, I said this before and I'll say it again. The actual rhythm is done within the organ itself. Okay, it's wired in. It's got a rhythm. It's going to beat. The heart's going to beat on its own. Right? You're going to breathe basically on your own. What's different is, are you going to increase it or are you going to decrease it? And that increase or decrease in the rate is controlled by the hypothalamus. Okay? Digestive tract motility. Are you going to be digesting your food or are you going to be waiting for a little bit? Rate and depth of breathing. Are you going to be breathing fast or breathing slow? Deep or shallow? And many other visceral activities we're not going to get into. So all these general visceral controls, things you don't think about, these are things that are involuntary, are controlled by the hypothalamus. It's a very important part of the brain. It's also the center for emotional response. So the limbic system, we talked about briefly before. One of the main parts of the brain involved in the limbic system is the hypothalamus. So you think about that. So you're saying that part of my brain is involved in emotion is the same part of the brain that is going to control my heartbeat and my breathing. Maybe that's why when I get nervous, I have an increased heart rate. Right? There is a true physiological response to emotion. And it's because the same part of the brain controls that. This is also where the idea of placebo effect comes about, which is if you have a general state of mind that you tend to think you're a healthy person, you actually are more healthy than someone who is persistently thinking they're sick. Ever heard of that? There's truth to that. There's a true physiological response to that. So if I give you a sugar pill when you have some horrible illness and I convince you it's not a sugar pill, but I convince you that it's a drug, a medication that we've been working on for years at Lilly, and I give it to you and you swear up and down it's working great, it could be. It really could be. It's because your mind made it work better. It's called a placebo effect. Okay? So again, connected through the hypothalamus. Regulation of food intake. So people don't always think about this, but it's true. When you eat food, you taste it. Not in your mouth, but also in your intestines. So you don't perceive that as taste, but your body perceives that as, oh, I've got a lot of lipids, a lot of fats. I'm going to secrete a hormone called GLP-1 that's going to cause my body to stop eating, to be satiated, to be full. So the idea of being full or being hungry is controlled by hormones, which are picked up by the hypothalamus and tell you, wow, I'm really hungry, or hey, I'm not hungry at all. GLP-1. It's a big thing, man. I'll leave it at that. Okay. Regulation of water balance and thirst. So you'll learn about this again in 102, antidiuretic hormone. We mentioned it briefly before. Antidiuretic hormone makes your body hold in water. It keeps blood pressure up. It's produced by the pituitary gland, among other things. And the problem with this is, of course, if you drink alcohol, it shuts down ADH release, and that makes you pee a lot, which is why you get dehydrated when you drink. So the part of the body, hypothalamus, that is controlling water balance and thirst, it is hypothalamus. You're kind of messing with that. Sleep-wake cycles. Now we're going to learn in just a few minutes that melanin is the hormone, but what actually carries out the sleep-wake cycles is actually the hypothalamus. So this is kind of your, I'm sure you've been there, just like I've been there, Saturday morning routine of you want to sleep in late. What happens? You wake up at 6 o'clock in the freaking morning, right? Why? Because you woke up at 6 o'clock in the freaking morning, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday comes around, you wake up at 6 o'clock in the morning, and you can't go back to bed. You've been there, right? Yeah. That internal clock, right? So it even seasonally. So that internal clock is done here with the hypothalamus as well. Control of endocrine system functioning. This is getting quite too difficult to say, but a lot of the hormones involved in the body are regulated from homeostatic balances through the pituitary gland and the hypothalamus. So we'll leave it at that. So very important things. The epithalamus, as I said, is kind of hard to see here, but you can really see more than anything else is the pineal gland. This is the epithalamus back here. The pineal gland makes melanin. Okay?
Melatonin, sir?
Oh, sorry, melatonin. Sorry, not melanin. Melanin is the dye. Melatonin. I said the wrong thing. So melatonin is the hormone that's involved in sleeping. Okay? So that actually makes it, and it's the hypothalamus that carries it out. That's the pineal gland, or pineal body, as some people call it. The brainstem consists of 3 parts, and I think this is the best picture here. So all these things here, by the way, see all these pictures? Here, here, here. None of that is going to be on the test. This, yes. But this, no. Those are all cross-section anatomy. I really don't care. So let's look at this one right here. So what we're looking at here is the last part. I'm sorry, I'm saying the last part. The cerebellum is the last part. The brainstem is the third part. Right? We have the midbrain, the pons, and the medulla. Midbrain, pons, and the medulla, or medulla oblongata. And right now, I'll tell you, anybody ever seen The Waterboy? They're wrong. Big surprise, movies are wrong. Okay? It has absolutely nothing to do with emotional response. And I don't know if alligators have a bigger one or not, but it has nothing to do with emotional response. So alligators are not honoring because they have a big medulla oblongata. Really what this is, okay, this is a passageway. It's a gateway. It's where you have a lot of connections. It's going to connect the top part of the brain to the cord. And so there's going to be a lot of tracks going through here. That's really what it is. It's a predominant number of tracks. And so you see a lot of these things is actually tracks. And you can see the little ridges that are here. Those are tracks. Okay? These are tracks. You can see them. So cuneate fasciculus, for example. Right? It's one of the ascending tracks. We can see that right there. So those are examples of, it's really what the majority of the brainstem is tracks. Now, there is some nuclei embedded in here. And that's what these pictures are showing, just so you can understand that there is some nuclei, like the red nucleus, for example, in reticular formation is another one. But I don't really care that you know all that. Okay? So we can see just some of the cross-section anatomy, but it gets way too complicated. I won't do that. Okay? So, you have the midbrain, you have the pons, and you have the medulla oblongata. That's what it is. Okay? Midbrain, pons, and medulla oblongata, or just medulla is fine if you want to keep it short. Okay? Or if you look at it from this picture, oops. Midbrain, pons, and medulla oblongata. Midbrain is red, the pons is light green, and the medulla oblongata is dark green. And then right here is where you have the spinal cord, and there's no real segment, as I said. Even though it shows it being purple versus green, it's not that defined. Now, another thing you see coming out of the entire brainstem here are cranial nerves. We're going to come back to that in just a little bit after break. Okay? But these are different cranial nerves, and you can see some of these coming out. And these are going to be controlling different parts of the face, or be sensations, or motor control for different parts of the face and the neck. So it's similar to what we see with the spinal nerves. These are called cranial nerves, and they all come out of the brainstem like that. Okay, goes into a lot of detail on the midbrain. Nothing. Including, I don't really care that you know the nuclei there. Substantia nigra and red nucleus you see on page 18. None of it. I don't know why I wrote it all down. I just went crazy. I did. I mean, I think I told you that, when I wrote these, I spent many hours doing it. By the time I got to chapters 14 and 15 out of 16, I just stopped editing. It just got tired, and I just kept going. I was like, oh, this is interesting, and my brain was not saying, you know what, they don't care. So, I apologize. So, it's there if you want to learn it on your own, but I'm not going to ask anything on it. Same with the pons. There's really nothing there to know other than just the general thing. The only thing I'll mention is on page 19, it says medulla oblongata, and you see a term there called choroid plexus. We will be talking about that in more detail after break. And the only reason it's mentioned there is because that's where you can find it. At least you'll see in just a little bit. It's one of the places you can find it. But right now, it's not something you need to know. So, anything else I'm going to mention here? No. Okay. The last part of the brain, the fourth part of 4, is called the cerebellum. Cerebellum, this is on page 21, cerebellum. You can see this is a picture of it right here. This is actually cut into it. I'll show you a different picture, a better one, here. Okay, because that's it before it gets cut, and this is when it gets cut. When you actually cut into it, you're going to do this today in the lab, and I really hope you do this in the lab. It actually looks like a little tree, like they call it arborvitae, tree of life. Okay, and you see how it looks like that? You have to cut into it to see that. This is like a little mini brain in the back of your brain, but it has a very specific function. We're going to talk about that. It does a lot of things, to be honest with you, which is why I go into a lot of detail here about all the things it does. But really, what I really care about is where it says cerebellar processing on page 22. This is really the big thing I think of. So, I told you before that our primary motor cortex, which is up here, right, is going to control our skeletal muscles. Very specifically, that's where the actual neurons are. That's where the actual cell bodies are. They're going to control these movements, right? And I told you that, at least with repeated things like typing or things that you can learn, right? We have that located roughly in the same area. And kind of showed you where, but roughly in the same area. What I didn't really explain to you is, okay, well, how do you walk? Okay? How do you put that all together to have a coordinated